Hi, welcome to Recitation 6. We are calculating derivatives today by using all the rules that we learned, including the chain rule, the most important one. I would say don't pay attention to the problem numbers in this presentation here. I deleted a few problems to make it shorter. But let's just focus on solving the problems. Here is the first one. Compute the derivatives of these two functions. Maybe we can call them A and B. Let's get right into it. What's going on in A? When you look at it, you should see that it's just a multiplication of three separate functions. It's the 3 to the x, the fifth root of x, and the tangent of x functions. Well, we haven't specifically talked about the product rule for 3 or more functions. We know how it works for 2 functions, but there's really no big secret here. You can think of it this way. Think of let's say the two first functions together. Let's imagine that's just one function, and then 10x is the other one. So if you want to apply the product rule between those two, first of all, this is how it's going to work. The 3 to the x, fifth root of x stays together, and the tangent is the other function. So we have these two terms right here, according to the product rule. And now for calculating this derivative in the first, in this product of 3 to the x and fifth root of x, we will again use the product rule. So to separate that out, there is going to be a prime on the 3 to the x and a fifth root of x, plus a 3 to the x alone with a prime on the fifth root. The whole thing times tangent. That's the first term, and I'm just copying down the second term. But once you distribute this 10x right here into the first two terms, you see that what you're left with in the end is just the sum of three separate things. Like this. And by doing it carefully, step by step like this, you realize how the product rule actually works when you have three functions in the product or more. Let's say 3 in this case, then, well, it's a sum of 3 terms where the prime gets applied to just one at a time. I think it's very clear right now. Now we just have to find these primes. Let's do that. Looking in the first term, 3 to the x prime. Please do not tell me that that's x 3 to the x minus 1. That's not true. I'm going to erase this, because that would be the power rule. You do that when x, the variable, is in the base, not in the exponent. This one right here is a exponential function. The derivative is ln of the base times the function itself, like this. And the others will just be copied down. Next, how do we differentiate fifth root of x? That's the same thing as x to the 1/5. Maybe I'll just write this down first before we compute that. So we see that this is going to be differentiated by the power rule this time. We'll do that in the next step. And the last term has the derivative of tangent. This is one of those that you should memorize, or you can compute it by the quotient rule. Tangent is sine over cosine, but it's going to give you secant squared. That's the derivative of tangent. Okay, so let me just copy down the two terms that we already have and finish computing the second one right here, where I told you derivative of x to the 1/5 is the same thing as, by the power rule, 1/5 times x to the 1/5 minus 1. Let me erase this exponent and calculate it. That's minus 4/5. And finally, 3 to the x, fifth root of x, secant square of x. Let's not worry about simplifying anything here. There isn't simplification, really. I guess you can factor a 3 to the x, but that's all. We don't do much more than that. So let's just leave it this way. That is the derivative. Now we can move on to item B. I'm looking at the function right now. It was cosine x ln x divided by 3e to the x minus 2x, derivative of this. Okay, here we don't have any functions inside of functions. There is no chain rule yet. This is just a quotient rule because it is a fraction. But when differentiating the numerator, we will also need the product rule because that's a product. So let's do this. If you remember how the quotient rule works, low d high minus, I guess I can scroll like this, high d low divided by low square. We have to compute this expression now. Okay, so if you're looking at the first term in the numerator, there is this factor of 3e to the x minus 2x, and then a derivative involving a product. So I'm going to compute that already. By product rule, when the derivative hits the cosine, that will give you a minus sign. Plus, when the derivative hits the ln, that's a 1 over x. That's the derivative with the product rule right there. The other term will be easier, minus cos x ln x. This derivative of a difference of this minus sign here really doesn't matter. You just take the derivative of each term separately. Derivative of 3e to the x is 3e to the x. Derivative of minus 2x is minus 2. Those are cases where you have constants in front of the functions. The constants remain. You just differentiate the functions. Now the whole thing is divided by, again, the square. Again, not worth simplifying this. This is a valid answer, unless the question asks you to simplify. But let's not do that. Let's move on to the other question. Problem 2. Find the equation of the tangent line to the graph of this function at the point with x coordinate 9. I have a little sketch of what the function looks like around that point. It's the red line. And the tangent line is this green line right here. We can see that it's going to have a negative slope. We need to find the equation of the tangent line. This is the equation of a tangent line. It goes through the point a f of a, where a is 9 here. The place, the x coordinate of the point where you want the tangent line to be based is 9 in this problem. And we don't know f of 9 yet, but we can find that easily from the function. So we're gonna need to know f of 9, and we're gonna need to know f prime of 9. We need the derivative. Let's actually compute the derivative first. So log 2 of, there's a square root of x squared minus 17 divided by x minus 8. This is the function. If we wanted to find its derivative, what is it going to be? In other words, f prime of x. How do you differentiate this function? Well, let's take this very carefully. You can see that you need a chain rule for this. There is something inside of a log, so it's functions of functions. So we know that we need this procedure of, let's call u the inside function. Let's call y the original function. It's log of u base 2. Finding dy du is very easy here. The derivative with a, if this was natural log, it would just be 1 over u. Because there is actually a base 2, then you also include ln of 2 in the denominator. This is the dy du term. Why are we computing that? Again, because the chain rule tells you the derivative that you want to find is dy du dx, but you need to find this du dx now. where u is given up here. So the u itself is not so easy to differentiate with respect to x, but it's fine. It's a fraction, and in the numerator, you also need a chain rule. It's a square root of another function. So we'll take this very carefully, but let's find du dx. Scrolling outside just so we can see the function. I'm looking at the expression for u, and I want to find the u dx. Low d high minus high d low divided by low squared. Let's compute this. Okay, so when you look at this expression, the only derivative here that's going to be more or less difficult to find is this derivative of the square root. This is again one that requires a chain rule. Let's do it on the side here. Let's use variable names that you haven't used yet. Let's say we call it w, the square root of x squared minus 17. We want dw dx. Well, let's call v the inside function, x squared minus 17. Then dw dx is going to be dw dv, dv dx. Now, that's easier to find. The w is square root of v. All right, that's the relationship between the two variables. So using those formulas, what is dw dv? The derivative of the square root function, you find that by the power rule, or you either memorized it, it's 1/2 root v. dv dx is also very easy, just 2x. The derivative of x squared minus 17 is 2x. So dw dx, the multiplication of these two terms, 2x over 2 root v. I'm multiplying the two variables, the two derivatives, and replacing v with its actual meaning. V is x squared minus 17. The one simplification you can do here is cut out the factors of 2. All right, let me circle all this thing. All of this was the derivative of the square root that's here. So now we can continue finding du dx. So we're going to have x minus 8 multiplying this whole derivative that we just found, minus this square root of x squared minus 17 times, what is the derivative of x minus 8? The derivative only hits the x, and that's a 1, whereas minus 8, the derivative of that is 0. So that's all you have for that second term, divided by x minus 8 squared. We don't have to simplify this, although we could. This is the derivative, du dx. Let's go back now. Why did we need to find the u dx? Remember that dy dx was still not the whole thing. So I'm going to write down again what we have so far. dy dx was dy du, du dx, where we actually found dy du is 1/ln 2 times u, if you remember. And the u dx is the one that we just found. The whole thing is divided by x minus 8 squared. Okay, and where u was actually square root of x squared minus 17. Divided by x minus 8 times, okay, now this whole other expression that I have in here. This is f prime of x, or dy dx. The largest portion of this question. We found the derivative of this crazy function. There's a lot of simplification that you could do here, but we don't really need that. Remember that all we wanted was to find f of 9 and f prime of 9 in order to find the equation of the tangent line. Let me write down f of x again here so we remember what it was. So what is f of 9? Log 2 of, you see that's going to be very simple. The square root, you're going to place 9 instead of x, so you have an 81 minus 17, that is the number 64, divided by 9 minus 8. So square root of 64, that's 8. 9 minus 8 is 1. So log base 2 of 8. This is the number 3. 8 is 2 to the 3. That's what a log means. Okay, so f of 9 is 3. And now f prime of 9, I'm looking back into this expression. I'm going to plug in x equals 9 in here. You'll see that it's really not that bad. ln2. So once again, this expression here, this fraction, we just computed that for x equals 9. That's the number 8 times x minus 8, 9 minus 8 is 1. So now let's look at this fraction, x over the square root, 9 over square root of 64 minus square root of 64 divided by, I guess, 1 square, 9 minus 8 squared. So you see, this is a number that we can perfectly compute. 1 over ln2 times 8 times 9 over 8 minus 8. This is like 9 minus 64 over 8. So minus 55 over 8, giving you the final answer to this problem. I mean, the final answer for this derivative, and now you're almost done. We have f of 9. We have f prime of 9. So the answer, the tangent line, y minus f of a, f of 9, sorry, this is 3, equals the derivative, the slope, times x minus a, which is 9. It was a big derivative. That was the point. I wanted to have a big derivative. So we practice all the rules that we know. But as we guessed from the picture, this is a negative slope right here. ln of 2 is a positive number because 2 is larger than 1. So this really is a negative number right here. And we are done with this question. Next, we have a much easier question right here. Suppose that two differentiable functions f and g satisfy this. We don't know what they are, but we know some of the values of the functions as well as one of the derivatives. Let h be this particular combination. Compute h prime of 0. How do we do this? Well, if you want to know the derivative at a specific point, like 0, really you have no choice. In most cases, you have to find it at a general point, x, from the formula. You differentiate the formula. Whatever you find, then you plug in 0. This is usually the procedure. So let's find h prime, the function h prime first. How do you differentiate this quotient? Let's use the quotient rule. So you want to do low d high minus high d low over low square. Now the derivative of each dx times f of x, this one requires product rule. Let's apply that. When the prime hits each dx, you just get each dx itself. And when the prime hits f of x, the each dx is not differentiated, but the f is. This is the product rule. Minus each dx, f of x, g prime of x, the whole thing divided by g of x squared. That's h prime. Now that you know h prime, you can try to find h prime of 0, which is what as the question asked. So I'm going to plug in x equals 0 in all of this. Each of the 0 is going to become 1. Now we just have to look back at the values that were given to us. I'm going to scroll back up so you can look at them. One of these guys we actually don't know. We don't know g prime of 0. But look at it is actually multiplied by f of 0. And look at what f of 0 is. It's actually 0. So this is why the question did not give us g prime of 0. We don't need it. So I'm going to plug in 0 for f of 0, -1 for g of 0, 3 for f prime of 0. G of 0 was -1. Right. So once again, this g prime of 0, we know it exists. It is a number. It is some number because they told us the functions are differentiable. Whatever this number is, though, if it's multiplied by 0, this goes away. And what is the final answer here? -3 divided by +1. So just -3. I hope this is good enough. This next question is very similar. Problem 5. Certain values of a differentiable function f and its derivative, f prime, are known. Here's a table, like f of 2 is -2, for example. And f prime of 3 is unknown. Now suppose that g is this function, f of x times f of x squared plus 1. Calculate its derivative at 2 points. So this is very similar. We need to find g prime first before we can calculate g prime at a specific number. Well, g is a product of two functions. So I'm going to go right away and apply the product rule. Like this. You see that when the derivative hits the second term, I'm not simply writing f prime of x squared plus 1. That's wrong for the second term here. It's supposed to be, I mean, this was the second term, f of x squared plus 1. The derivative hits that entire thing. That's differentiating that term. And the derivative of that is something that requires a chain rule because it's a function f of another function, x squared plus 1. So let's actually find that by the chain rule. How do we do that? Well, let's call y the whole thing. Let's call u this inside function, x squared plus 1, so that y is f of u. Now, du dx is easy, that's 2x. And dy du, if y is f of u, dy du is f prime of u. We don't actually know what this function f is in this problem. We don't have a formula to write down here, but in symbols, this is what it becomes. So the dy dx is the product of these two terms, 2x f prime of u, where u is equal to x squared plus 1. So this was this derivative right here that appeared in the second term of the g prime. I'm going to replace that in there now. We have g prime equals f prime of x, f of x squared plus 1, plus f of x times this derivative that we just found. That's the formula for g prime of x. Now we're good to go with the table that we wanted. The question was asking for g prime of 0. So I'm going to plug in x equals 0. 2 times 0 times f prime of 1. Plugged in x equals 0. So for example, the x squared plus 1 becomes 1. But you see right here in the second term, 2 times 0, that's a 0. This whole expression right here goes away. I think there are at least one of these numbers here. We don't know that, but we don't have to know them because this term goes away entirely. This is just f prime of 0 times f of 1. where if you look back in the table, this is 2 times 3. I don't want to scroll back up. I have it written down on the side here. So the answer is 6. Now g prime of 2, do the same thing. Plug in 2 into the formula for g prime. So f prime of 2 times f of, what happens when you plug in 2 for this expression, x squared plus 1? That becomes 4 plus 1, or 5, plus f of 5 times 2 times, sorry, f of 2 times 2 times 2, this is the 2x term, times f prime of, again, 5. This is right. If you look back in the table, it will give you a -9. Just try to plug in those numbers yourself to see. So we found the g prime of 2. Moving on. Problem 7. Actually not 7, but whatever. All right, you may have noticed, we never have absolute values in these problems where we're trying to find derivatives. Normally, we don't need derivatives of functions involving absolute value. The reason for that is the absolute value function itself is not differentiable at the number 0. Remember, the graph of it has a sharp corner. But sometimes you actually do want to differentiate a function having absolute value, like this. And what you want to do is analyze the two separate cases, when that number is positive and when that number is negative, the number inside of the absolute value. So this question is saying, verify that the derivative of the function ln of absolute value of x is equal to 1 over x for all x different from 0. Obviously, you cannot apply this to x equals 0. ln of 0 would not exist. But they want us to verify this for all x different from 0 by analyzing separately the two cases, when x is on the positive numbers and when x is on the negative numbers. This is usually how you do this. When you're taking a derivative of a function that's defined piecewise in two separate pieces, like absolute value is in these two pieces, you want to analyze it separately in each piece. So for example, if x belongs, this by the way is the symbol for belongs. If x belongs to the positive piece, then absolute value of x is just x. So the derivative that we're trying to find is just the derivative of ln of x. We know that, that's 1 over x. So the formula checks out. We already knew that. The interesting case here is when x is negative. Now the function that we're trying to differentiate is actually ln of minus x. Because absolute value of x is minus x now. And what happens here, this is a chain rule. You have two functions. You have ln of another function, the another function being a very simple one, minus x. Let's find this by chain rule. Let's call it y. Let's call u the inside term, the minus x, so that y is actually ln of u. This will be a very easy one. Du dx is minus 1. dy du is 1 over u. So dy dx is 1 times the other. It is minus 1 times 1 over u, where u is minus x. That's how you write this derivative in terms of the original variable x. And we can simplify the minus signs here. It is just 1 over x. So the derivative that we wanted to find, again, gives you a 1 over x. Checks out exactly what the question wanted us to do. You see that if you did not know the chain rule, all you know is the derivative of ln is 1 over x. If you did not know the chain rule, when you look at this, I think you would be inclined to say it is 1 over minus x. But that's wrong. That's not how you take a derivative of a composite function. You have to do this chain rule, and the minus signs will go away. Next one. This is also going to go by quickly. Compute these higher order derivatives. 3 items here. I have higher order derivatives, always using different notation for them, but it's all the same, higher order. Let's look at the first one. There are 5 primes in there if you look carefully. We want to differentiate 1 over x 5 times. We have no choice but do it one by one. So let's do this. How do you find derivative of 1 over x? The quickest way is to rewrite this as x to the minus 1 so that you can use the power rule. Minus x to the minus 2. You could also have done this by the quotient rule, but usually you don't want to do a quotient rule if it is just a number on the top. But you can do it. And if you also want to rewrite this as a fraction, that is minus 1 over x squared. But let's keep it in this form actually. That's the quickest one for us to keep doing this. So for example, if you want 2 derivatives, take this derivative that you already found and take a prime again. Let's be careful now. First of all, the minus sign can go outside of the prime. And now you can use product rule, sorry, power rule again. Minus 2x to the minus 3. So this actually gives you a plus 2x to the minus 3. Moving on, 3 primes. We're going to take this 2 primes that we already found and take another prime. The 2 is a constant. We can write it outside. And now this x to the minus 3 can be differentiated again by the power rule. 2 times minus 3 is minus 6. So there's no secret here. We'll keep doing this. If you want to find another prime, what is going to happen to this expression? The minus 4 will multiply the minus 6, producing a plus 24. And the power loses yet another exponent, minus 5. Finally, 5 primes. The minus 5 multiplies the 24, giving you negative 120, and you lose another exponent, minus 6. You see that it's quite interesting. The signs keep changing, plus, minus, plus, minus. The power keeps losing 1 and 1, and the numbers that you see in front, you may recognize them. Those are the factorials. 3 factorial, 4 factorial, 5 factorial, if you know what that means. If you don't worry. You should be able to solve the problem anyway. Now B, I'm writing it down again. B gave us a function where it's not told to us, but it's implicit. A, B, C, and D are constants. The variable is x. The numbers A, B, C, D are just constant. And we want to find, remember what this notation means. The second derivative, this is the same thing as f prime prime of 0. So this is a case where they're asking for a derivative at a specific number. What you have to do, you have to find that derivative first. Find f prime prime of x. You have a formula and then you plug in 0. So let's first find the second derivative function. Let's find f prime and then f double prime. This is a quotient rule. Let's just write it down. Low D high minus high D low over low squared. You see that there is actually a cancellation that happens here when you take the primes. Derivative of ax plus b. Keep in mind that a and b are constants. So they're just like numbers, like 2x plus 5. When you differentiate this, only ax will have a derivative, and the derivative will be that constant, a. Similarly here, the derivative of cx plus d is c. Now, it's not a good idea to leave it like this, because if the simplification is very easy and very helpful. You see that there is an a times cx, but then there's minus c times ax. those are going to go away. The only thing that's going to be left is AD minus BC. This is the first derivative. But keep in mind, we wanted the second derivative. You don't plug in 0 yet for x. You want to find f double prime of x. You want to find the formula for the double derivative. So we'll try to do that now. F double prime will be the derivative of this expression. What is the best way to find this derivative? You can use the quotient rule again. It will give you the right answer, but I'm going to do a different thing. AD minus BC, remember, that's just a constant. It is just a number. We can move it outside of the derivative, like this. You actually only want to differentiate this part, 1 over cx plus d squared. And then multiply by that constant. To do this derivative, I'm going to use the chain rule. Let's call that y. Let me call cx plus d the inside, the inner function, so that y is 1 over u squared. Using this, you can find a derivative dy dx by the chain rule. dy du, the derivative of 1 over u squared by with respect to u is done by the power rule. 1 over u squared is u to the minus 2. So this gives you minus 2u to the minus 3. And du dx is just c. Derivative of cx plus d is the constant c. So dy dx is c times negative 2u to minus 3, or c times negative 2 cx plus d to the minus 3. This maybe a different color here, so we can leave that. This is that, this prime. We still need to multiply that by AD minus BC to find F double prime. So we have found F double prime. AD minus BC times C times negative 2 CX plus D to the negative 3. Yes, I just want to double check my calculation. Okay, now we are ready to plug in x equals 0. Remember, the question wanted f double prime of 0. So really it doesn't simplify much. We basically have a 0 in place of x. So only the d part survives. And that's your final answer, which, by the way, probably you want to do something like this. There's a constant minus 2 times c, minus 2c. The other constant is ad minus bc. And then the d is raised to minus 3. So for example, you might want to divide by d cubed. I'm just pointing out a different way to write this expression, but that's already a perfectly fine final answer. Last part. All right, now the last item. This item is asking for the 100 derivatives of this polynomial of degree 60. How do we do this? Do we want to take 100 derivatives of this expression? Certainly not. We just have to try to understand what is going to happen. Let's imagine that we try to find 100 derivatives. You have to start with 1 to see what happens. We know how to find this. I'm just applying the power rule. The plus 4 will go away. The derivative of plus 4 is nothing. This is one derivative. You see that the coefficients are getting larger, but you're also losing powers, as you do with the power rule. If you wanted to differentiate again, double prime, let's differentiate this one more time. The 59 will come in front of the 60. We don't have to compute this big number, but the 59 power will lose 1 unit. Similarly, the 29 power will lose another unit. So basically, what's going to happen after you differentiate this, let's say 30 times? What's going to happen with this term, the 5t to the 30? After differentiating 30 times, the exponent is losing 1 power every time, 29, 28, 27. After 30 times, that will be a 0, which t to the 0 is 1. So the entire thing will have just a constant in here. There will be no more t anymore. And if you do another derivative 31 times, the derivative of that big constant will be 0. So that's going to happen to that term. So only the first term will survive. But the same idea applies to that. If you differentiate this first term 61 times, it goes away. It becomes 0. And we do have enough derivatives here. We have at least 100. I mean, we have 100. So really, the d, I'm going to write it this way. This differentiating 61 times gives you 0. And then after that, doesn't matter how many more times you do that. If you go up to 100, you're just differentiating 0 again and again and again. That is a 0. So you should remember this, by the way, when you have a polynomial. If you differentiate the polynomial enough times, at least 1 plus the degree, then all the terms will go away. You eventually find just 0. So that's your answer.